What if I told you your CPU doesn't just execute instructions, it predicts the future? Not occasionally, not sometimes, millions of times, every single second. And when it gets that prediction wrong, your entire system pays the price. Your apps slow down, your games stutter, your code runs just a little bit worse. But here's the part almost nobody realizes. Modern CPUs depend on these predictions so heavily that without them, your computer wouldn't just be slower, it would feel completely broken. Some estimates suggest performance would drop by 10, even 100 times. So the real question is, how does your CPU predict the future? And what actually happens when it fails? Because once you understand this, you'll start seeing performance differently. You'll start noticing things most people never do, and you'll realize something slightly unsettling. Your computer is constantly guessing. Let's start simple. At its core, your CPU executes instructions, one after another. Load this value, add these numbers, store the result. Simple, predictable, safe. Until suddenly, it isn't, because every real program eventually reaches a moment like this. If something is true, do this. Otherwise, do something completely different. And right here, the CPU hits a wall, because it doesn't know what comes next. And that uncertainty is a problem, but not for the reason you might think. It's not about correctness. The CPU will always figure out the right path eventually. The real problem is time, because modern CPUs are not designed to wait. They are designed to move continuously, relentlessly, without stopping. And to understand why that matters, you need to understand something called the pipeline. Imagine a factory. Not one worker doing everything, but many workers, each responsible for one step. One fetches instructions, another decodes them, another executes them, another writes results back. And instead of waiting for one instruction to finish, the CPU overlaps them. Dozens of instructions, all in flight at the same time. This is how modern processors achieve speed, not by doing one thing faster, but by doing many things at once. But there's a hidden assumption here. This entire system only works if the CPU knows what instruction comes next. And with branches, it doesn't. So what happens? Let's slow this down with a quick mental picture. Imagine you're reading a book, but every few sentences you encounter this. If the character chooses the door, go to page 200. If not, go to page 50. You can't read both paths at once. You have to choose. But choosing takes time, and time is exactly what the CPU cannot afford. So instead of waiting, it does something bold. It guesses, it looks at the branch, and makes a decision before knowing the answer. And then it keeps going, as if that guess is correct. This is branch prediction, and it's not just a trick, it's the foundation of modern CPU performance. But here's where things get interesting. At first, CPUs weren't very good at this. Early processors used something called static prediction. Simple rules, for example, backward branches are probably loops. Forward branches are probably not taken. It worked, but not very well, because real programs are messy, unpredictable, full of patterns that simple rules can't capture. So engineers started asking a different question. What if the CPU could learn? What if it could remember what happened before and use that to predict the future? And that's exactly what they built. Inside your CPU, there's a structure called the branch history table. Think of it as memory, not for data, but for behavior. Every time a branch executes, the CPU records what happened. Taken, not taken. And the next time it sees that branch, it uses that memory to predict the outcome. Now here's the first twist. You might think one previous result is enough. If it was taken last time, it will probably be taken again, but real programs don't behave that cleanly. Sometimes a branch flips occasionally, And if the CPU changes its prediction too quickly, it becomes unstable. So engineers added something subtle but powerful. Instead of 1 bit, they used 2, a tiny state machine, a 2-bit saturating counter, which means the CPU doesn't immediately change its mind after one mistake. It needs to see a pattern, consistency, confidence before switching its prediction. And suddenly, accuracy improves dramatically. But then came an even bigger realization. Branches are not independent. They influence each other. The outcome of one branch can depend on what happened several branches ago. So the CPU started tracking global history, not just individual decisions, but sequences, patterns across time. And now we're entering the territory of modern predictors, G-share, tournament predictors, hybrid systems. These combine multiple strategies and choose the best one dynamically. And this is where companies like Intel and AMD spent decades competing, because improving prediction accuracy by even 1% can translate into massive real-world performance gains. But now we reach a critical point. Prediction alone isn't enough, because knowing what might happen doesn't speed things up unless you act on it. So the CPU takes the next step, and this is where things get slightly unsettling. It starts executing instructions based on the prediction before confirming if it's correct. This is called speculative execution. The CPU is now living in the future, running code that might never actually happen. Let's pause here for a second. Think about what this means. Your processor is actively doing work that could be completely useless. Entire chains of instructions executed only to be discarded later. And yet, this is one of the biggest reasons your computer feels fast. Because when the prediction is correct, everything flows perfectly. No delays, no interruptions, maximum efficiency. But when it's wrong, everything collapses. And this is where the cost appears. The CPU must flush the pipeline, discard speculative results, roll back to a known correct state, and restart execution. And this recovery is expensive. On modern CPUs, a misprediction can cost 10, 15, even 20 cycles or more. Now here's the second twist. That cost doesn't just affect one instruction, because while the CPU was speculating, it filled the pipeline with dependent instructions. So when the prediction fails, it's not just one mistake. It's a cascade, a chain reaction of wasted work. And suddenly, a single wrong guess ripples through the system. Now let's make this real. Imagine a tight loop in a game, running thousands of times per frame. If the branch inside that loop is unpredictable, the CPU keeps mispredicting. Again, and again, and again, each time paying the penalty. And suddenly, your frame rate drops. Not because your GPU is slow, not because your code is bad, but because your CPU kept guessing wrong. Now here's something even more fascinating. Developers actually optimize code based on branch prediction. They write code in ways that make branches predictable. They reorder conditions. They remove branches entirely. They use techniques like branchless programming, all to help the CPU guess correctly. Because one good prediction is often faster than any optimization you can write. But now we arrive at something even more surprising. Because this entire system, branch prediction and speculative execution, led to one of the most important discoveries in modern computing. A vulnerability, a flaw, not in correctness, but in behavior. In 2018, researchers revealed something shocking. A vulnerability called Spectre. It showed that attackers could manipulate the CPU's predictions. They could train it to make specific guesses, and then exploit speculative execution to access data that should never be visible. Even though the CPU eventually realized the mistake and discarded the results, the side effects remained. tiny traces, in the cache, in timing, in subtle differences that could be measured. And those traces were enough. Enough to extract secrets, passwords, private keys, sensitive memory, all leaking through speculation. Not because the CPU was broken, but because it was too advanced, too aggressive, too optimized. And this forced the entire industry to respond. Intel, AMD, ARM, operating systems, browsers, cloud providers, everyone had to rethink how CPUs behave. Mitigations were introduced, barriers, fences, new instructions, microcode updates, but every fix came with a cost, performance, because now the CPU had to be more careful, less aggressive, more conservative in its predictions. And that brings us back to you, because every time you open an app, scroll a page, compile code, run a game, your CPU is making predictions, constantly, thousands, millions, billions of them, every second. And most of the time, you never notice. Because it works, because it's right, because everything feels smooth. But occasionally, just for a moment, something feels off. A tiny delay, a brief stutter, a micropause you can't quite explain. And deep inside your processor, that's the moment a prediction failed. A guess about the future turned out to be wrong, and the CPU had to recover. So next time your system slows down, even slightly, remember this. It might not be your software, it might not be your hardware, it might just be one bad guess. Because modern computing isn't just about executing instructions, it's about predicting them, anticipating them, staying one step ahead, and doing it so well that you never even realize it's happening, unless you look closely. And now that you do, you'll start to see it everywhere. Every smooth interaction, every delay, every moment of speed, driven by something invisible, something constant, something quietly shaping your entire experience. Your CPU, guessing the future, and sometimes getting it wrong. And what happens next is even more surprising.